In this video we'd like to show you a little bit about the angular momentum, which is called moment cinétique in French or Drehimpuls in German. Now, before looking at rotating bodies, let's first consider translation. Now we know that if different forces act on a body, on a single body, then this body is considered to be in equilibrium, so it's moving in a straight line at constant speed, or it is at rest. But that can only happen if the vector sum of all forces is equal to the null vector. Similarly, if these forces are not in equilibrium, so they add up to something which is not the null vector, then, according to Newton's second law, this body with this mass m is going to be accelerated according to Newton's second law. You can rewrite this law by considering the quantity of momentum, quantité de mouvement in French, impulse in German, which is just the mass times the velocity vector. Now, if we sum up all the forces, they will tell us how this quantity and the momentum of the body is going to be changing over time. So to summarize, we can say that if forces act on a body and these forces sum up to something which is non-zero, well, that means that the momentum of the body is going to change. It can change either in direction or in magnitude. Now let's talk about rotation. If we consider this case here, where we have a force in one case pulling down here and trying to make the lever rotate in this direction, then we have a second force on this side which is trying to make the lever rotate in this direction. All this is happening around an axis of rotation which we call delta. And then we already know that we will have to consider the torque of the force, the moment de force, or the Drehmoment in German. Well, the torque of the force is defined as the magnitude of the force times the length of the lever. And then if we sum up all the different torques, all the different moment de force, we have to consider that some of them will be called positive and the other ones are negative. And so if we sum them all up, we will have equilibrium. And this looks very similar to the equilibrium of translation that we've seen before. Now, if we want to generalize this rule, we'll have to consider the torque as a vector quantity. So let's first look at the torque of force F2, for example. This force is trying to make the body rotate in this direction. And to fix the direction of the torque vector now, we'll consider the right-hand rule. The direction of rotation is assigned to the fingers, and our thumb needs to be parallel to the axis of rotation. The axis of rotation is the line going through the body here. This is the axis of rotation. So in this case, the torque of F2 is going to be represented by a vector coming out of the plane of the body, like this. This is going to be the moment around the axis delta of the force F2, and this is a vector. We'll see later on what the magnitude of the vector is. Let's first look at F1. This force is trying to make it rotate in this direction, so if you use the right-hand rule around the axis delta, the torque vector is going to be pointing inwards into the plane of the body, and that's going to be the torque around the axis delta of force F1. And this is again a vector. And we can do the same thing for F3. F3 tries to make the body rotate in this direction, and that means that the torque vector is also going to be pointing into the plane of the body. So this is going to be representing the moment around the axis delta of force F3, and it's again a vector quantity. There's a mathematical way to define the torque of a force. With what we know now, we can rewrite the equilibrium of rotation equation by simply saying that the sum and the vector sum of all the different torques around axis delta of all the different forces need to be equal to the null vector. And this now looks really similar to what we had for the equilibrium in translation, where the sum of all forces had to be equal to 0. But we could extend this and we could say that if the sum of the forces is not equal to 0, well then there's going to be a change in a quantity, which we call momentum, over time. And now we're going to extend the same thing here by saying, now if the torques as vector quantities don't compensate each other, I shouldn't have put a 1 here, so don't compensate each other, well there's going to be a change of a certain vector quantity that we'll have to define. There's going to be a d over dt here, a change of a certain vector quantity x that we will have to define now. Now the quantity that I want to show you is the angular momentum, moment cinétique in French or Drehimpuls in German. And we try to derive it in the very simple case of a point-like body moving at velocity v with a mass m, and it's going to be positioned at a certain time at a distance r, at a position r from the axis of rotation, and for simplicity we'll consider that there's only a single force acting on this body. Now if you look at Newton's second law, then we can say that the force is equal to the rate of change of the momentum, knowing that the momentum of course is equal to m times the velocity. If we now multiply on both sides of the equation by using a cross product r cross this equation, then we'll end up with r cross f on one side of the equation, which is equal to r cross dp dt. So r cross dp dt. On the left hand side, you immediately see that this is going to be equal to the torque of the force. So this is the torque around axis delta of the force as a vector quantity. That's quite easy. On the right hand side, you can show that this is going to be equal to the rate of change of the quantity r cross p. So the position vector cross product with the momentum. And this is going to be defined as a new quantity which we call the angular momentum. So now the torque around axis delta of the force F is going to be equal to the rate of change of a new quantity which we call the angular momentum. And for a point-like particle, the angular momentum is simply defined as r cross p. And we end up with something very similar to Newton's second law for torques, and this time it's the sum of all the torques is going to be equal to the rate of change of the angular momentum. Now let's apply this new law to a very simple case where the sum of all torques acting on the body is equal to 0. You can have that in the case of an ice skater. Here there's no net torque acting on if we neglect friction. Well, in that case we can say that the derivative of the angular momentum with respect to time is going to be equal to 0. Or another way to say this is that the angular momentum is going to be conserved in magnitude and in direction. Now what does this mean in this case? If you look at the figure skater, well, she has her axis of rotation here, and if we look at the arms, well, we can consider there's a certain radius of rotation for the arms, an effective radius. This arm is moving backwards like this, while this arm is moving to the front. Both of these contribute to the total angular momentum of the ice skater, which, if you use the right hand rule, is always going to be pointed upwards. So she has a certain angular momentum. And we know that if no net torque acts on her, that this angular momentum needs to be conserved. So for the second case, where she has pulled her arms together, the angular momentum will have to stay the same. But, as we see, her arms are much closer together, so the radius r is much smaller, and the only way to conserve the angular momentum is to increase the momentum of her arms. Another way to say this is that the angular velocity is going to be much higher in the second case than in the first case. So omega prime is much larger than omega. And that's how an ice skater can actually accelerate her rotation speed. Finally, I'd like you to have a look at this small exercise here for a point mass that is moving on uniformly on a circle, that this angular momentum needs to be equal to this, where omega is the angular velocity. And also think about the torque of the different forces that may be acting on a body doing a uniform circular motion.